Hello, smart people. This is our 16th lecture on this tensors, and most probably we have discussed about what is basically that affine connection. So how it relates the two coordinate systems when we talk about the example of a free fall of an object. तो मैंने आपको एक example बताई थी in my previous lecture. So if you talk about the free fall of some object, or if you talk about if I am going for skydiving, I am putting a book in my hand, if I release it, so with respect to me, so it has that zero acceleration. And when we differentiate it by using that mathematics, and we saw that this, like if we talk about the derivative of a tensor, so you should get some another tensor but of same rank. But what we observe that तो जो हमारी rank है, so we are getting some additional term, so that is because of the curvature of space time. So as I already told, I have discussed it, I repeated it so many times. So this is basically which basically relates, like if you talk about a book which is falling under free fall, so there is no resistance of air. So this book, so it has some coordinates, like if you talk about, if you are viewing a book, so you are saying that it has some coordinates x, u, so that means in that space-time curvature. So it has four components, one time and three space components. So how you can relate that these coordinates of that book with respect to the earth, so that means how you relate these two coordinates, so that's basically given by this affine connection, right? So हम देख सकेंगे, we can see that this affine connection, how it relates to the gravitational field. So that's our today's lecture, right? So this was basically what we have discussed, is that this is our affine connection, that is t lambda mu, so that's partial x lambda mu partial. So this is capital lambda, capital X, and this x mu is basically function of, so this x mu, it can be a function of x mu and x mu, right? So it's a function of these coordinates, right? And in addition to that, so this was basically what we have discussed in our so far our previous lecture was concerned, right? And in addition to that, so there was one more problem, that if we talk about this, so if we talk about some limiting case, so because we already know that the field of the earth is very weak compared to, if we talk about, अगर हम compare इसको करेंगे with the field or the gravitational field of the neutron stars or black holes, तो वहाँ पे जो gravitational field वो बहुत ज़्यादा है, because if you talk about, we can go upstairs in presence of the gravitation, because we can, so that means the gravitational field is very weak, right? And we can see that in the limiting case, this affine connection, this tau lambda mu nu, it basically corresponds to our gravitational field, right? So that means today's lecture is about that, if we talk about that Newtonian limit, so that means at some limiting value, if we take some limiting value, so this affine connection basically gives us the gravitational field, right? So today's lecture is about the, if we talk about the Newtonian limit, right? So today's lecture is that. So in Newtonian limit, suppose we are saying that a particle falling, suppose particle is falling in a system of generalized coordinates, right? So अगर एक particle fall हो रहा है in some, it has some coordinates, some x mu, we can say that, but in presence of gravitation, right? So neglecting the effect of this air resistance, so there is no that additional force, only the one force is that is because of the gravitational field. So that means we are talking about the free fall of an object, we can say that, right? So in that case, if we write now, so let's write now, so that means we are saying that there should be no influence, right? So if we write our equation, because we know that if we say that the particle is falling with the zero acceleration, like in the example that I quoted in my previous lecture, the skydiving example, I can say that. So we have seen that the book is falling with the zero acceleration. So we can say that in similar to that, so we can have some kind of similar equation. So what we have, so that that, so we can have this kind of equation, that is d2 x lambda. We get this kind of equation. Like if we talk about the free fall of an object and use the property of that product rule, differentiate the equation, and you are getting this kind of equation. And this is very clear. So the first part corresponds to our acceleration of the object which is falling under the effect of this gravitational field, right? And in addition to that, so there is no other this I resistance we neglected that, so there is no other force present in this case, right? Now, so this is our first part, that's this first term that corresponds to our acceleration. And similarly, well, let's have a look on the second term. So this is what we have discussed in our previous two lectures. So this is again our affine connection, and these two terms. So first term corresponds to our acceleration because this is the derivative of that this generalized coordinates, you can say that, which is in the space time, because मैंने आपको बताया था if we talk about the book, I am looking at a book, so I am saying that it has some coordinate x mu. So x mu it is basically in space time, so that means it has time as well as the space components. So this is basically our the acceleration. So this is sorry, so this is our velocity, and again you have this is the velocity, 4 velocity, you can say that, right? So these two terms, or you can rewrite this term as, okay. So that means this corresponds to our 4 velocity. Right? So why we are saying that it is 4 velocity? Because it has 4 components. That's time component and the space components, right? So that's why it's called 4 velocity. So we're adding one more component because working in the space time. So it's that we're working in the space time diagram. I can say that. So that is our the fourth component. This coordinate is our time. So that's why we can say that we are working in the Minkowski space, right? So this is our 4 velocity, or you can say this is again the 4 velocity of a particle which is falling under the effect of this gravitational field or effect of gravity. Now, so if you have a look on this equation, right, and this equation resembles the free fall of an object, we can say that. So this equation resembles, if you write now, so this resembles the equation. Okay, so this resembles the this equation where so we can say that the force is due to the gravity here, right? Okay, or you can rewrite this as, so this is our that F minus mg equal to 0, because our acceleration will be due to the this will be the gravitational this will be the acceleration due to gravity here, right? So that's why I put here in the stop here I put here g, right? And this is our again that equation. If you compare this equation with this one, so this is our equation A. Right? Now if you compare these two equations, right? So okay, instead of that, so we can okay, let's write one more stuff here. Okay, so they can rewrite this as, okay. So this equation can be written as, that is, what there, that is, right? And if you check, so let's have a look on this equation. So we have one more equation, that's equation A. So if you compare this equation A with equation B, so जो equation A है, we have this term. So this is again that acceleration, right? And this term is our it is because of that gravitational field, right? So if you compare these equations, so that means this term corresponds to a gravitational field. So that is basically this one. So this g will be equal to that one, right? So we can say that the first term is our acceleration. This is our acceleration, and this term corresponds to our gravitational field. So which is further equal to, we can write that, so that is that minus g will be equal to that, so that's equal to that tau lambda mu. Okay. So this is what we have, what on after comparing this equation A and equation B, right? So we're writing that gravitation is basically this one, right? So what's the physical interpretation? As I already told you, if you talk about the physical interpretation of that affine connection, that is T lambda mu, right? As I already told you, if you talk about the gravitational field, so it's very weak. So it's very weak compared to if you talk about the this field of due to neutron stars, or if you talk about the this okay, the field in the black holes. If you talk about the gravitational field, right? So the field in case of these neutron stars or these black holes, the field is very weak here, right? So that means I can now I can get in the limiting case. If you talk about the limiting case of this equation, so this affine connection, it corresponds to our gravitational field, right? So that means this so we can say that it provides a kind of the boundary condition because it connects us. If you consider the limiting case and the static case, so it corresponds to a gravitational field, right? So that means it basically provides a kind of boundary condition in the it basically provides a boundary condition on the tensor theory of gravity, right? So it basically, if you go in the limiting case in the low limit, so this affine connection corresponds to our gravitational field, right? Okay. So let us rewrite now. So if you rewrite this term, now if you write now what is the velocity components here. So this velocity component, if you write that what is u mu, so u mu will be equal to, so that is equal to, gamma, right? So this is if you talk about in Minkowski space. Because Minkowski space, so it has that, so this will be our that 4 velocity, right? And it has that time as well as the space component. Now if you put that c equal to 1 here, so you can write that u mu equal to, by choosing that c equal to 1, that's gamma into 1 comma, right? With c equal to 1, and what's gamma here? So gamma equal to, okay. Now if you talk about for a falling particle, if you talk about the falling particle, the velocity is less than 1, right? So that means if you write now, so for a falling particle, so if you choose now u will be less than 1, right? So that means if you talk about the non-relativistic speed, so that means this is basically if you talk about the non-relativistic, right? So in non-relativistic speed, the velocity will be, so in the limited case, you will be less than 1, right? So in that case, what will be our that gamma in that case? So Lorentz factor in that case, अगर हम non-relativistic particle देखें, so relativistic are those particles are traveling with the equal to the velocity of light, like photons. So these are traveling with the velocity of light. But if you talk about the non-relativistic particles, right? Some object, you take a book, right, and skydiving case, right? So I'm repeating it many times, so I'm bound to repeat it, right? So in that case, you are saying that it has some acceleration or it has some velocity, and you are saying that it is not traveling with the velocity of light. So we are considering that if we consider non-relativistic case, it can have some velocity, right? So here we are assuming that in non-relativistic speed, if you consider that the velocity will be less than 1, right? And what about that Lorentz factor in that case? So this gamma will be equal to 1, right? So that means the forward velocity will be simply that u mu will be equal to simply that is equal to 1 comma v, right? So 1 corresponds to, because c we have chosen that c should be equal to 1. So in that context, we are choosing that c equal to 1, so it will be equal to 1 comma v, right? And what about that u naught? So what will be u naught? So if you want to calculate the time component of that velocity, right? Forward velocity, right? Time component. So that is basically equal to, that is dx u dx 0 by deta, because you know that our u mu is, so if you remember that our u mu is, that is equal to deta, right? So putting that mu equal to 0, so you will get this thing, or this will be equal to, right? Because what I did here is dx 0, so that is equal to c dt, right? So when you are writing that x0, x1, x2, x3, right? So if you remember that, we are saying that if we put that x0, so this will be ct x. So this is our four-dimensional space, right? So that means instead of the time component, I am writing c into t. But here c is equal to 1. We are choosing that c equal to 1. So this will be dt by dt. So remember, these are two different times, right? So one is that proper time and another is improper time. So this one corresponds to a proper time. So and it remains invariant if you go from one frame to another frame. But this is related to which frame you are talking about. Agar maybe I am moving in a car. So my time interval when I'm in a car, so that's basically called improper time. Proper time is that time which is same for the person who is at rest or the person who is in some new frame of reference, right? So that's called the proper time. So these are two different times. So dt by deta, right? So this is our improper time and this is called proper time. Now, so this is basically how you write the time component of that force velocity. So that's dt by. And similarly, if you talk about that, the three components of that velocity, like ux, uy. So the different components of velocity component means ux, uy, and uz. Because as I already told you, when you talk about the non-relativistic speed, so there the velocity is less than 1. So that means that those components will be zero in that case. Right? So we can write them. So what will be our that uk? U mu. So that is basically dx mu, right? Right. You can write that. Then what is our u here? Uk. So that is our dx k. Right. So okay. So this is for when you talk about the non-relativistic speed. Let me repeat it once again. So I am talking about that when the velocity is less than 1. So in that case, if you talk about the velocity components, that's ux, u, and uy, because we assume that when u is less than 1, so we can say that this total three components, because k is that 1, 2, 3. So that means 1 corresponds to our x component, 2 corresponds to y, and 3 corresponds to z component, right? Okay. So let's calculate now, because we are calculating here for the limiting case. So let us talk about now. So if you rewrite that equation, so we have that equation that is dx, so d2x lambda. So this was our other equation, right? And we basically so these are well-known terms to you. Huh? So if you put that one when mu equal to 0, because for mu equal to 1, 2, 3, so this velocity component will be 0. So only the time component will survive here. So that way, if you put mu equal to 0, mu equal to 0, right? So if you put here, so you can write here, this will be equal to. Okay. So what is u0 and v0? So these are basically that dt by deta, right? So this will be equal to 1 in what case? Wherever t will be equal to, small t will be equal to capital T, right? Because we already know that, okay, let me check that equation. Okay, so this equation. So if t equal to tau, right? So in that case, this term will be equal to 1, right? So that means we can, okay, so, okay, this equation. Okay. So when you put that t equal to that tau, so u0 will be equal to 1 and v0 will be equal to 1, right? So that means this equation can be written as, so this equation will be equal to, that is, right? Or when we consider that our small t is equal to capital T, right? Proper time equal to improper time. Okay. Now, okay. So first let's calculate this term, because So if you put in general, so this lambda mu nu, so this is equal to, if you so this is equal to that 1 by 2 g lambda rho partial upon partial x mu. Right, this is equal to, okay. So this is, so while from it comes, so I will explain that. So before, so this is basically how you write this FN connection in terms of that Manco schematics, right? Because so these are that partial derivative variation with respect to that coordinate transformation, variation with respect to these coordinates, and these are that Manco schematic, right? And so let us first calculate what we, how we can calculate this T lambda, right? So in order to calculate that, so let us write that. So this, if you remember that this tau lambda mu nu, so this is what we have discussed so far. It is basically the transformation of efficient connection, right? So which basically connects the two coordinate systems, right? So you can say that this is basically the transformation. Okay. Now my question is that, if can we say that is that affine connection, that T lambda mu nu a tensor or not? So we need to check that, because if you take its variation, you are basically going from some one frame. So first frame is that a book which is falling in free fall under the effect of gravitation. So the second coordinate is that the surface of the earth, right? So what I'm saying that if you see that this connection between these coordinates, that's basically given by this T lambda mu, that's affine connection. So we need to say that, we need to see that whether this T lambda mu is a tensor or not. So to answer this question, so let us make the two ground frames here. So in order to check that, so we need to check that this T lambda mu is a tensor or not. So how we can, so we have discussed so many times. So if you remember that, so how we can define a tensor? So we're saying that if something goes like that transformation, so we have some, like we are going some from x mu to some x nu, right, with some transformation matrices. So that's basically called a tensor, right? So it should follow some transformation rule, like you talk about the Lorentz transformation, right? So that means, so it should go like that, right? So in order to define that, so how this, whether we can say that this affine connection is a tensor or not, so we need to choose, we are choosing the two ground frames. So that means we are choosing from, so we are going from some x mu to some x mu prime. So these are basically that, we are saying that the two ground frames, so these are basically the two ground frames. Okay. Okay, if you calculate now, तो अब हमें देखना है कि we are going from some frame x mu to some x mu prime, right? तो हमें देखना है कि what is the, how this affine connection connects these two, right? So we already know that. So we know that if we write the affine connection for some coordinates lambda mu, so that's basically given by, that is some partial x lambda, partial x, some so it should be some alpha here, partial 2x alpha, partial x. But here, so we need to choose, these are our two coordinate systems. So that means we are basically going from some x mu to x mu prime, right? Or from some mu prime to some, from some prime to some unprimed system, right? So we can write this as, so this will be equal to that T lambda prime mu mu. So that will be equal to, मैंने क्या किया सिंपली आई तो ये मैंने जो फिन कनेक्शन यहाँ पे दिया आई एम राइटिंग इट फ्रॉम सम प्राइमरी सिस्टम राइट सो दैट्स व्हाई आई पुट हियर प्राइम एंड हियर इट शुड बी देयर प्राइम so we can write this okay so this is it because what we read here so this is basically that which basically connects that old coordinates with the new coordinates so these are the new coordinates new are the new coordinates right and these are our old coordinates right so this is what we have seen so far so that the affine connection can be written in this way right and in the present case हमने consider किया कि हमें देखना है कि whether this affine connection is a tensor or not so for that case we are saying that we are going between the two ground frames from some x mu to x mu prime and see the how this how we can write this affine connection between these two frames so this is very clear you can write it in this way right from some primer to some unprimer right so we can rewrite this term. So let us rewrite this term as, so that means I can write that T. So this is, so I'm basically rewriting, so this same stuff what we have, what I wrote in my previous slide, so you just check. So यहाँ पे the same equation what I wrote here. So this is it. This is same this. Okay. So we can rewrite this term as so let us derive this as so this will be that partial x sorry so this is small x so let me write it here x prime by lambda okay so this can be written as partial x rho okay so यहाँ पे मैंने क्या simply I multiply and divide by partial x rho right okay so rest is it okay so you can rewrite this term as so let us rewrite now we are basically we have two terms where this variation we need to take the variation of this thing with respect to this right so I can rewrite this as let me rewrite this term as so this will be equal to that partial x prime or you can rewrite here okay let me write it here so instead of this equation I can so in order to skip one step so we can minimize one step by taking that partial by partial x prime u right. Inside will be that is equal to that partial x alpha. So you just check whether it is that. तो यहाँ पे मैंने क्या किया तो ये वाली टर्म ठीक है because यहाँ पे मैंने multiply and divide by किया partial x rho से right and similarly in this I basically take one differential out so that's partial by partial x prime mu तो इनसे रहना चाहिए partial x by partial mu so again I multiply here by partial x rho partial x sigma by into partial x sigma right so rest is same right because this is partial x mu from inside out and partial x prime mu is inside right and this is same so you can cross so you get the same term what we have in our first step okay right. So I can rewrite this term so we need to so let us split this term first so I can rewrite this term as so this will be equal to I can rewrite this as partial x prime mu so this is saying what I wrote here. Now we differentiate this term. So differentiate first this term, then differentiate this term. But when we differentiate this term, because this is capital X, it is basically function of that some small x, right? So it is a function of those new coordinates, right? So we can rewrite this term as, so this will be, we can rewrite this as that partial to x alpha. Now, in denominator, we should have that partial x prime mu and partial x rho. Now, instead of that, I am writing here partial x tau and partial x rho, right? Okay. So I am writing here partial x term, partial x root, and you can write here that partial x term, partial x prime mu, and partial x root. Partial. Okay. Uh, okay. Sorry. So you can because I need to write one more term, which is coming from. Okay. So this is first term plus. तो ये पहली वाली टर्म है जब हमने डिफरेंशिएट किया इस वाली टर्म, राइट? एंड सो दिस इज बेसिकली दिस टर्म बिकॉज यहाँ पे मैंने पार्शियल को एक्सप्लेन और यहाँ पे मैंने डिवाइड किया पार्शियल का टाउ, तो पार्शियल का टाउ इन द न्यूमरेटर यहाँ पे, तो ये कैंसिल हो जाएगा, यू गेट द सेम टर्म एंड दिस वाज ऑलरेडी दैट पार्शियल का रो एंड दिस इज पार्शियल का टाउ, पार्शियल का प्राइम यू एंड सो यू जस्ट चेक. Okay, now second term is if you differentiate the second term now. Okay, so keeping first term constant and differentiate second term. So that is if you rewrite this term as that's partial x alpha. Okay, and this is partial to x, sorry. So this is small x here. Yeah? So because the space was very, so यहाँ पे जगह नहीं थी, तो that's why I write here this denominator, that is you put this first constant, right? And so that is basically this term and differentiate this term, that is partial to x sigma and this term, right? So यहाँ पे हम तो why you don't write so what we have what we have how we modify the first term by dividing by this. So because this is small x here, right? Capital X is a function of that small, right? So that's why यहाँ पे हमने simply differentiate किया this term को and this was constant. By using that the product rule in case of differentiation, right? Okay. Okay, so let us rewrite this step. So we have two steps. So this term is this and this term is this thing, right? So we can rewrite this as, so let us write first term. So first term is that is partial x prime lambda. So this is our first term. तो ये जो मेरी ये वाली टर्म है, तो यहाँ पे मैंने क्या किया, ये टर्म मल्टीप्लाई किया इस टर्म को, right? So this is, so let us first see so whether we can get some kind of some affine term from here, and similarly then we will solve the second term. So इसको multiply किया इससे, so that's what I wrote in this slide. So this is our this thing and this is our first term, right? So we can modify this term. So if I rewrite this term as, so this term I can write as so I take this term and this term out and I can put this term inside. So this will be that, you can write that partial x root. So if you have a look on this expression, so this is again that affine term, right? Because we have some that, so if you check, so if you go on the first slide, so let me check that. Okay, this term. Huh? So, so not this one. Oh, yeah, one more. Huh? So this one. So t lambda mu is written this way, right? We have some जो यहाँ पे superscript होगा वो यहाँ पे आएगा, right? And जो subscript यहाँ पे आएगा, it will come in this derivative, right? And we can have that alpha, you can put that mu, beta, gamma, so it's up to you, right? Because it's the dummy indices, right? So you can write anything, right? But this is very important. In subscript, you need to write it here, right? So this is saying what we get from here. So this is again that if in connection. So that means in subscript we have rho. So it will be equal to. So this term will be equal to that's partial x square lambda. Right? So this is very clear, right? Because using that this is F in connection because rho is here. So this will be in the subscript of this term. And here it is tau and sigma, right? Tau and sigma here comes here, right? So these are F in connection. So we can rewrite this term. So इस term के बदले I can write that last term plus this term, right? So I can rewrite that our equation will be. So we can write that. Now, okay, let's have a look. So, okay, so this is basically we solve the first term, and similarly, if you solve the second term, so second term is that's partial x lambda, lambda. Okay. Okay, so let me check if I'm right. So, okay, so this should be what's next? Oh, that's correct. That's correct. So this small x here. Yeah? So remember, so this was small x, right? So let us solve this term. So let's first rewrite this term. So because here you can combine this and this term, right? Because this is alpha here, alpha. So you can write this as. So this term can be you can rewrite this term as. So this term will be equal to that's partial x prime lambda. So okay, right. So this term is our that delta conical term. So this term is our that delta rho sigma, right? Because this term will because this and this will contract, so you get rho sigma, right? So that means if you put that before that rho equal to sigma, so this delta of rho sigma should be equal to 1, right? So you use it here. So this term will be equal to that partial x prime lambda. Okay. So यहाँ पे मैंने क्या करना है? I need to write that instead of rho you can write sigma, or instead of sigma you can write rho. So this will be equal to that partial x prime lambda, partial x rho, and partial 2 x rho by partial x prime mu, partial x prime. Okay. Because when you put that rho के बदले हमें लिखा है sigma, so that's the same. Okay. So this is we wrote that second term, we wrote the first term. Let us use it in our that previous equation. So ये हमें कहाँ पे use करना है? So we need to use it in this equation because this is our first term when you take the product of this with this term, and our second term is when you take the product of this term with the second, right? So let us use it in this equation and see what sort of equation we are getting from here, right? Okay, so let's rewrite. So we can write now. So our that t prime lambda mu will be equal to. So that's equal to partial x prime lambda. Partial x is sigma, right? Partial x prime mu t p rho tau sigma plus. Okay. So let us check if it is right. Okay, so it is rho here. Okay, that's correct. That's correct. Okay. So this is what we get from here. Okay. Now, if you check now, so this first term. So if you write that, therefore that lambda equal to rho, tau equal to this sigma, right? So that means if you put that lambda equal to rho, tau equal to that mu, or rho sigma equal to mu, तो वहाँ पे क्या हो जाएगा? So we get the same term. So that means it is not transformed like a tensor. Right? So it's sorry, it is transformed like a tensor in that case, right? Because when you put these in this is same. So that means if you put that our lambda should be equal to rho, because this term will be equal to 1, and when you put that tau equal to mu or that sigma equal to mu, so in that case, so this whole term, so this should be equal to 1. And this affine term, you will get that t lambda prime mu, right? So you will get the same. So that it spoils the whole physics. So it supposes this whole physics from here, right? So that means, so but we have this additional term here. It basically we can say that this additional term prevents this tau, this affine term from transforming like a tensor, because again later if this term will be equal to, if you put these are equal, so it transforms like a tensor in that case. But this term, because we have some additional term here, right? So this term helps us to prevent it, to prevent this tau, this affine connection by transforming like a tensor. It's not a tensor, right? So it is simply the connection between the two coordinate systems, right? So because our project was that, so whether this affine connection is a tensor or not, right? Because so we have some second term, it basically prevents it from transforming like a tensor. Otherwise, if you have only the first term here, so it's like a tensor. It's transformed like a tensor, right? Okay, because we have some this transformation matrix, right, and the same this, right? So you are going from some mu prime to some mu, from primed to some unprimed system with some transformation matrix, like we have some Morgan's equation, right? So that means, so because of this second term, it basically it's not a tensor, right? This affine connection is not a tensor, right? Now, if you rewrite this equation, so we know that if you rewrite this equation, so we can rewrite this equation, this term. So this term, because this term is clear, so we can rewrite this term as that's partial x prime lambda. Okay, right. Okay, I can rewrite this term as, so this term I can write as, so I can rewrite this term as that's partial x lambda, partial x rho, this is lambda here, and partial x rho upon partial x prime. Right? So this is very clear. So यहाँ पे मैंने because these differential they commute with each other. We can write that first. I can take this differentiation and this, or you can write this and then this, because they commute with each other, right? So differentials commute with each other, right? So I can write it this way. Now, if I have to call this term, right? Because we have rho, so this will be equal to that delta of lambda nu partial x rho partial x prime. So that means, so we can write then, so that means we have this partial x prime lambda, partial x rho need to, let us differentiate this equation. Okay, so we'll differentiate this equation, and if you differentiate this equation, differentiate with respect to x prime mu, right? So we need to differentiate it with x prime mu. So this term will be equal to, so when you differentiate it, so this will be partial to x prime lambda by, or you can, okay, let me write one more step because I cannot sit up here. Okay, so I think I should have, maybe in coming lecture we'll discuss that because it is already late. So in coming lecture we'll go on onwards from this lecture onwards, and we'll see that how this in the limiting case how this affine connection corresponds to gravitational field. So I hope you are getting these lectures. So if any suggestion or if any confusion in these lectures or the previous lectures, so feel free to comment me in my comment box. Thank you very much.